Chapter 8, Section 2, Gaussian Elimination. Gaussian elimination is one of the most fundamental methods for solving systems of linear equations. Named after mathematician Carl Friedrich Gauss, this method systematically transforms a system of linear equations into a simpler form that can be easily solved. Gaussian elimination is highly efficient and can be applied to any system of linear equations. This section will explore the steps of Gaussian elimination, provide its mathematical basis, and show how it helps solve systems of linear equations. Gaussian elimination is a method for solving a system of linear equations by transforming the system's augmented matrix into a row echelon form using a series of elementary row operations. Once the matrix is in row echelon form, back substitution is used to find a solution to the equations. Specifically, using Gaussian elimination, we can solve a system of linear equations following the three steps. First, write the augmented matrix. Step 2. Transform the matrix into row echelon form. The third step is to perform back substitution. Let's explore these steps one by one. To understand the process of Gaussian elimination, let's solve a system of linear equations step by step. Consider this system of equations. Step 1. Write the augmented matrix. First, we write the augmented matrix for the system of equations, including both the coefficients and the constants on the right-hand side. As the first step, we transform the matrix into row echelon form. So, first, create zeros below the pivot in the first column. The first pivot is the leading entry in the first row. In this example, it is 2. To transform this matrix into row echelon form, first, we aim to create zeros below this first pivot by applying row operations. So, let's eliminate the entry below the pivot, that is, 4 in the second row. Subtract 2 times the first row from the second row to create a 0. This operation results in this matrix. Next, eliminate the entry below the pivot, that is, -2 in the third row. By adding the first row to the third row, we can create a 0. This operation results in this matrix. The next pivot is the leading entry in the second row, which is -5. We aim to create a 0 below this pivot in the third row. Eliminate the entry below the pivot, 8 in the third row. Add 8 by -5 times the second row to the third row. It equals R3 minus 1.6 times R2. The resulting matrix is in row echelon form, with zeros below all pivots. Once the matrix is in row echelon form, we can use back substitution to solve for the variables, starting from the last row. First, solve for z from the third row. As the third row represents, -5.4 times z equals 3.4. So, z equals -17 divided by 27. Next, substitute z equals -17 by 27 into the second row to solve for y. Multiply through by 27 to clear the fraction. Let's solve for y. It shows y equals 8 by 27. Finally, substitute y equals 8 by 27 and z equals minus 17 by 27 into the first row to solve for x. Simplify the fractions. Multiply through by 27. Then solve for x, and it shows x equals 47 by 27. Thus, the solution to the system is x equals 47 by 27, y equals 8 by 27, and z equals minus 17 by 27. Gaussian elimination is a technique for solving systems of linear equations. By transforming a system into row echelon form and using back substitution, we can find the solutions efficiently and accurately. In the next section, we will explore more advanced method for solving linear systems, LU decomposition. Thank you for watching. Please thumbs up and subscribe to my channel.